Math372, complex analysis, lecture 30, new position for the tripod. We will see how well it works. All right, so what I want to do today is talk a little bit about inversion. So all of our proofs, coming down to the proof of the central limit theorem, they come down to, at the end, we're looking at a moment generating function or characteristic function, and it looks like that of a Gaussian. And then we want to say, aha, it must be the Gaussian. Well, the problem is, what if we have two different things that are mapped to the same Fourier transform? That'd be bad. What if we have two different densities that have the same series of moments? And it turns out there are two such densities. So I will include that example in the additional comments. It's in the notes that you're supposed to be looking at for this section. But there are two probability densities that have the same integer moments. The moments are going fast enough that it does not uniquely determine a probability distribution, which is good because we have two probability distributions with those same moments. So it should violate, in some sense, goodness. All right. This should remind you of the Taylor series we had of the function e to the negative 1 over x squared. It's functions like this that make analysis hard. This is where you want to say, well, let me look at a good space of functions. And if I look at a good space of functions, then I should have something unique if I know the moments. And in some sense, this goes very well with the Thanksgiving thought. I hope none of you had to use it because of a painful Thanksgiving holiday with family and friends. Can we define the space where this integral operator acts in such a way that it's well behaved and that we do have an inversion, that all the steps are well defined? So here's the question. Say f and g have the same Fourier transform. Are they equal? So there's a huge theory about inverting the Fourier transform. I'm not going to go too much into that. I want to just give you a little bit of a sample. We're going to look with the Fourier transform. There's really not much of a difference between the Fourier transform and the Laplace transform. It just comes down to where you put your I. So once you allow your parameter to be complex, they're essentially the same except for how you start to initially define them. Okay? So this is the equivalent to saying, assume h equals f minus g, and maybe now h hat of y is always 0. Does this mean that h is identically 0? That's what we would love to have. And so recall we're looking at, h hat of y is the integral from minus infinity to infinity of h of x e to the negative 2 pi I xy dx. Okay? So there's a lot of different ways we can be looking at things. What I want to do is I want to look at the more moment formulation of this, because that's what we were doing for the central limit theorem. You can convert from one language to another. And so let's go back and let's assume we have two nice densities with equal moments at a sequence Rn such that Rn converges to R, and these will be all non-negative. Is this enough to prove that the densities must be the same? And of course, right now I'm being vague on, what do I mean by nice? You typically start off by saying, well, let me just do the argument, and let's see as I go along, what do I need? So the nth moment, or the rth moment, we'll do the rth moment. So I'll have this go to, because I don't necessarily want that to be the same as the r there. We'll do it at mn for the moments. There we go. So the rth moment will be the integral from 0 to infinity of f of x, x to the m dx. And we often put a prime here to remind ourselves that this is the uncentered moment. I'm not subtracting off the mean. And here I'm going to be assuming the densities are on the interval 0 infinity. Yes?
X to the r.
Ah, thank you. It's x to the r. Thank you. So I'll look at the rth moment. And then similarly, I could look at the rth moment of the other one. And so now we can see this notation is not quite sufficient. So let's do maybe mu fr, mu gr prime would be the integral from 0 to infinity, g of x, x to the r dx. Right. And so now we have two densities. We have the definition of the moment for each, and we're going to assume that these agree along a sequence of r's that accumulate. It was working before class, and now it's not. All right. So let's let h equal f minus g, and then we can look at mu h n prime. Sorry. And this would be the integral from 0 to infinity of f of x minus g of x, x to the r dx. Does this integral exist? So first you always have to be careful. Does the integral exist? Well, these two integrals exist. The functions f and g are non-negative. So if I use the triangle inequality, this is less than or equal to f plus g in absolute value. So we know mu hr prime is less than or equal to mu fr prime plus mu gr prime. Okay, so the integral at least exists. What do you think we want to do?
Is there something preventing us from just expanding out and separating the integral into that one minus the other one?
Well, we can do that and we'll just get 0. So we can do that. So, well, we know it's 0 along that special sequence. So what would you like to use? What theorem would you like to use?
You just have to show that that function of r is holomorphic, and you can show it's constant.
So we have to show this function is holomorphic. If we can show this function is holomorphic, then so I'm writing it as a better way of writing this maybe is mu h prime of r, or if you want, of z. Think of this as a complex valued function. The whole point of this is to show how much notation matters. If I write it like this, integral from 0 to infinity, f of x minus g of x, x to the z dx, is it a little bit more clear that this is something I should be differentiating? Is it less clear over here that this is something I should be differentiating? And if there's a difference, you need to really think about why is one way easier than another. And when you're doing mathematics, how can you rewrite things in such a way as to increase your likelihood of detecting what you should be doing? As soon as you see we have a sequence, you should be thinking points of accumulation. And then as soon as you think about points of accumulation, well, what do I need to make a points of accumulation argument work? I need something to be differentiable. All right, so what would I love to do? I'd love to differentiate under the integral sign. Okay? There are rules that allow us to determine when you can differentiate under the integral sign. If my functions f and g have nice decay, it's not going to be a problem. And so we would get, and now the notation is really bad, so I'll write d by dz, because sadly we're using primes in the notation of mu h prime of z would be the integral from 0 to infinity f of x minus g of x. Now, what will the derivative of x to the z be? X to the z log x. And so in the notes, I go through it very slowly as to why this is differentiable. What you can do is you can evaluate this at z plus h, subtract it off at z, divide by h, and take the limit as h goes to 0. And then as long as you have nice decay, you'll be fine. As x goes to infinity, we might be a little bit worried because this is polynomially growing, but we're assuming the moments exist. So because the moments exist and these functions are non-negative, if we just put in absolute values, everything is fine. It's only the real part of z that controls the growth rate. So this will be fine. All right, so now we have a function. And then we show that this function is differentiable. And now we can use points of accumulation. So now by points of accumulation, it's constant. So now as function is 0 along mn, which accumulates to m, have identically 0. So by using points of accumulation, we now know that this function must be identically 0. So no matter what value of r we put in, we get 0. And so now we're down to what seems like an intuitively obvious statement. I have a function, I integrate against x to the r for any r, and I get 0. Is the only way to do that to have this being identically 0. And so this is something that needs to be proved. So there's a lot of different ways you can try to approach something like this. The first is to notice that we're doing things right now with moments. We could do a change of variables and convert this to something about Fourier transforms. So this is really close to what's called a Laplace transform. We'll see in a moment. Let's let x equal e to the t. And then we would get mu h prime of r would be the integral from minus infinity to infinity, because when x equals 0, t equals negative infinity, we would get f of e to the t minus g e to the t. And now x to the r would become e to the t r, and then dx is just going to be e to the t dt. So if I define new functions, if I let f tilde of t be f of e to the t e to the t, and g tilde of t be g of e to the t e to the t, this is the same as the integral from minus infinity to infinity of f tilde of t minus g tilde of t e to the tr dt. And if I now take r to be, say, iy, that's a Fourier transform. And so then I'd be getting the Fourier transforms of this everywhere is 0. So really, if you can do it for one, you can do it for another. The question becomes, will these functions be decaying? I'm now multiplying by an e to the t. Good or bad? Bad. But I'm evaluating my function at e to the t. So my function has to have decay to be integrable. And so now again, it could be decaying, spike up over a very small window, decay, spike up even higher over a very small window. This is why analysis is either fun or devilish, depending on your point of view. So we would need some assumptions about the decay rates of f and g. And that's why in the notes I talk about functions being in the Schwartz space. I talk about a certain level of exponential decay that's necessary to make all these arguments work. And you can now begin to see where that's coming from a change like this. Okay? I'll end with just one short remark, because there is one case when we can quickly prove everything is fine using results we've already done in class. And if I can do a simpler case using results we've already done, rather than doing a more advanced case, given that the semester is ending fast, I would rather do the simple case. So we have some beautiful theorems about Fourier series. Let's imagine that we're in a situation where our functions have finite support. So imagine somehow we know that our functions only live on the interval 0 to whatever. Without loss of generality, what is whatever? 1, right? Change variables so that whatever equals 1. Okay? So assume f is, well, we'll do h, is such that h hat is 0. And h lives on 0, 1. So we have h hat of y is the integral from minus infinity to infinity, h of t e to the negative 2 pi I ty dt. Well, this is the same integral from 0 to 1 h of t e to the negative 2 pi I ty dt. And I'm just using h for my difference of my two functions. So let's imagine, here's 0, here's 1. Let's imagine h is nice. Imagine there's a point where h is not 0. Actually, let's draw it a little bit bigger. So here's 1, here's 0. Here's some special point, let's call it x0, where my function h is large. Large could be 10 to the negative quadrillion. It's not 0. If we assume our function h is continuous, then it has to be non-zero in a small region about this. And if you want, we can choose a very small band here such that its value is at least 99% of what its value was at the center. So I could have a really small band here. And in that small band, I won't move too much. So I'll call this distance 2 delta this way and negative 2 delta that way. We know we can write any nice continuous function as a sum of sines and cosines. Right? Whose theorem can we use? There are two right answers. We could use Fourier. And who else could we use? Not Fourier. Fourier never proved it. So we could use Fourier series. So whose theorem uses Fourier series? We could use Dirichlet. So Dirichet's theorem tells us we can write any continuous differentiable function as a sum of sines and cosines, and the sines and cosine weights are going to be the Fourier coefficients. Fourier's theorem is essentially the same, except it's a weighted sum. I don't really care if it's a weighted sum or not. I'm just trying to come up with a good function. So I want a function that's essentially 0 everywhere up until maybe minus delta. Then it spikes upward and comes down. And so if we juggle things just right, because everything is integrating to 0, we can force this integral to be non-zero. So maybe if this has height epsilon, we want our spike to be maybe delta, maybe 1 over epsilon delta. Because the width over here is going to be like 2 delta. The height is going to be epsilon. So this will give me an area of 1. So what I can do is I'll have my function basically just blowing things up. Here's x0 minus 2 delta. Here's x0 minus delta. I'll have it ramp all the way up from here to being 1 over epsilon delta. Now if I do it like this, this is not continuous. Fine. I'm sorry, it's continuous, it's not differentiable. I could do it maybe parabolically or cubically around here if I want to smooth things out. Or I could say, let's just use Fourier's theorem. What is your preference? Let's just use Fourier's theorem, exactly, right? Do we care about this function? No, this is just an auxiliary function to help us with the proof. So the real reason I want to do this stuff today is I really want to talk to you about how you prove these results and focusing on what matters and what doesn't matter. This is just an intermediate function to help us get to the result. At the end of the day, do we need this function? No. Think back to Lagrange multipliers from Calc 3. How many of you saw Lagrange multipliers in Calc 3? How many of you did not see Lagrange multipliers in Calc 3? Okay. Wow, okay. All right, an aside. I'm sorry, you are not allowed to graduate with a math degree without seeing Lagrange multipliers. It's just one of those things that can't be done. I almost forbade somebody to graduate a few years ago because she had not seen Star Wars and she was a CS graphics person. And as a CS graphics person, you've got to see Star Wars. All right, so Lagrange multipliers, it all comes down to I have a constrained maximization minimization problem. I have a function to find on a surface, and I want to figure out where is it largest, where is it smallest. I want to figure out what are the candidate points. So in one dimension, you check the endpoints, and then you look at places where the first derivative is 0. So in higher dimensions, if I have a nice space, I use is the gradient 0 in the interior. And then on the boundary, what I do is I look and see, so here's my surface. Here's the normal to the surface. So if maybe this is the surface g of x equals c, this over here is the gradient of g. And then if my function has something that's the gradient of f in this direction, if the gradient of f does not align with the gradient of g, I can break this vector down as to something tangent to the surface and something perpendicular to the surface. And that tells me that if I flow just a little bit in this direction, my function will increase. If I flow a little bit in that direction, the function will decrease. So I can't be at a maximum or minimum unless the gradient of f is in the same direction as the gradient of g. That doesn't mean that I will have a maximum or minimum there. It just means it's a candidate. So you need to solve the following system of equations. G of x equals c. That's the equation of your surface. And then the gradient of f at some point x equals some multiple of the gradient of g at the point x. And if you think of x as having n components, you have n plus 1 equations. N equations, one from each component here, and then one more equation here. And you have n plus 1 variables. You have the x variables, 1 through n, and you have lambda. And then this is where you place Sesame Street. One of these things is not like the other. One of these things just doesn't belong. At the end of the day, do we care about the value of lambda? No. It's often useful to find the value of lambda to then find the value of the x. But at the end of the day, it's the point x we care about, not lambda. Lambda is a helping quantity. And that's how you need to view a lot of these constructs. I'm just trying to create a function to help. And if I have this function, which is essentially almost 0 here, and then I get a nice thing like this, I can force my integral to be small all in through here. And then I can force the integral to be large over here, and that's going to contradict the fact that it has to integrate to 0. Okay? If you want a simpler version of this, just imagine you have a continuous function. And say, what do I have to integrate a continuous function against and always get 0 to be able to conclude that my continuous function is identically 0? Or you might ask for a slightly stronger condition. Maybe I want my function to be continuous and differentiable, and trying to figure out what conditions do you need. All right, so this is about all I want to say. It gives you another example of why we care about Fourier series, why we care about Dirichlet. Yes?
Can you go back over what exactly you just proved?
Sure. So we were looking at, imagine we have a function on 0, 1, and assume that its Fourier transform is always 0. So for us, I'll actually take my y's to be my integers n. So what this is telling me is all the Fourier coefficients are 0. Then what I'll do is I will approximate this function with a sum of sines and cosines. And each one of them is going to then integrate to 0 against h. But if I do the integration directly, well, I know the integral is now going to be large. It's going to be approximately 1, or at least 1. So the idea is we know that the integration term by term is 0, but somehow when we combine it at the end of the day, we get an integral that's about 1. So there must be a contradiction. And the contradiction is the fact that we assumed that there was a point where the function was not 0. So it's a good idea to go through this and try to put in the details and make it vigorous. But I just wanted to give you, a big picture sense of what's going on, what are the issues in the subject. It really all comes down to, at the end of the day, if the transform of something is 0, did you start with 0? What's the space of things that get mapped to 0? Because if two things are mapped to the same thing, we'll just subtract them. This is why when we did accumulation points, we often said, I have a sequence of points where the function is 0, rather than I have two functions that are equal along a sequence of points, because I can just subtract. Okay, so there's a small split in the department as to whether or not differential equations should be required for graduation. How many of you have not taken differential equations? Okay, it's unlikely that the people who want differential equations to be required will be able to gather enough support to put that requirement in this year. and not grandfather anybody in. I know Williams is about to change some of the distribution requirements, but there's always the grandfathering in people. So you only have so many math classes to take. Which classes should you take? Is differential equations a worthwhile class to take? What techniques do you want to know to be able to solve differential equations? So I'm not going to motivate why we care about differential equations. Basically, they allow us to, well, okay, I guess this is, I will only briefly motivate why we care about differential equations. You can model things. Most things are not static in time. Most things change. Thermostatics is a very boring subject, right? You want things to vary, and you want to, well, as this varies, how does this vary? And differential equations allows you to solve these. Most differential equations can't be solved exactly, and a lot of times we can't even prove whether or not a differential equation has a solution. We often appeal to, well, this differential equation models the planets, and the planets have motion, or this models a fluid, and the fluid has motion, therefore there must be a solution. This is an invalid argument, because you do not know that the differential equation actually models the physical object. You just assume, hope, seems reasonable, whatever phrase you want. At least 2 of the 6 open clay millennial problems, which have a $1 million price tag on it, involve finding solutions to differential equations. It is an extremely important area in mathematical research. And so what I want to do is I want to show you a little bit about how the Laplace transform can be used to solve differential equations. You could do an entire unit on this in differential equations. I'm going to just briefly describe what's going on, reduce it to an inversion problem. I'm just looking at the big construction truck going by and making sure they don't destroy my office. Just making sure that they actually tear down the right building. There's all these stories of doctors who remove the wrong organ from a body. With all the construction going on campus, I'm worried. All right, Laplace transform. So f is nice. The Laplace transform of f, evaluated at the point s, is the integral from 0 to infinity of f of t e to the negative st dt. Okay, good. So there's a lot of different ways you can define things. I'm going to do my stuff like this. My function f is going to be on 0 infinity. If I want my function to be on the interval negative infinity to infinity, I can just do a change of variables. I can let t equal e to the u. So this is not that restrictive of an assumption. Then the question is, for what values will this converge? Well, one nice thing about having this just as an integral from 0 to infinity is if s has positive real part, I've got exponential decay. And it's quite likely that this integral will exist. So maybe if f is not growing too rapidly, as long as the real part of s is positive, this will converge. You can begin to see why complex analysis will be useful for this, because we might want to consider s as a complex variable. So the first thing when you have a transform like this is you ask, well, what are the transforms of standard functions? And so you've seen tables of integral transform, tables of integrals. They've got tables of integral transforms. You put in a function and out comes a new function. We talked about kernels before. This is the kernel kst equals e to the negative st. We've seen these with convolutions. We've seen these with Fourier series, with Fourier series. Kernels like this are extremely useful. So I'm not going to go through and calculate a bunch of Laplace transforms. I will leave that as an exercise for you. And now the question is, why do we care about this? So part of this is leading up to some of the stuff for the end of the semester. So on Wednesday, we'll do fractals, and we'll do the SCS. I want to make sure there's enough time, so I want to do a shorter unit on Wednesday. On Friday, I'll either do random matrix theory, or I might do the Heisenberg uncertainty principle. Depends on the mood, which could make sense for the Heisenberg uncertainty principle. What you will see in the Heisenberg uncertainty principle is the physics is that somehow position corresponds to this operator and momentum corresponds to this operator, and you can view them as functions where they're Fourier transforms of each other. And then there's this identity about how spread out a function is and how spread out its Fourier transform is. They both can't be concentrated too much. The more you concentrate one, the more spread out the other becomes. And one of the things that makes Fourier transform so nice, we've seen the Fourier transform of a convolution is the product of the Fourier transforms. We've seen this with moment generating functions, with characteristic functions. This is one of the reasons we love Fourier transforms. It converts integration through convolution, which is painful, to pointwise multiplication, which is nice. The problem is, at the end of the day, you then have to invert. And that's where you pay the piper. Let's look and see what goes on for the Laplace transform. Let's look at the Laplace transform of f prime at s. So we have the integral from 0 to infinity of f prime of t e to the negative st dt. And for now, just assume anything you want to make things converge. Okay? Any thoughts as to how we should attack this? Integration by parts seems like a really natural thing to do. We've got an f prime. We want to somehow relate the Laplace transform of f prime to the Laplace transform of f, so let's try to integrate by parts. So let's let u equal f prime of t. I'm sorry. This should be dv is f prime of t dt, and u should be e to the negative st. Then v would be f of t, and du would be negative s e to the negative st dt. Okay, so now using that, so I go over that like this, I can now make it work. I'll get the Laplace transform of f prime at s. So I have my boundary term, which is the uv, so it'll be f of t e to the negative st at 0 and infinity, and then I'll have minus v du. Well, the two minus signs will cancel, so I get plus integral from 0 to infinity of f of t e to the negative st dt, and I'll pull out the s. All right, so when I put in infinity, what should I get?
0.
I should get 0. I should have enough decay that this is going to be 0. And then when I put in 0, I'll just get negative f of 0. And then what's the second term going to be? It's just the Laplace transform of f at s. So we get the Laplace transform of f prime at s is negative f of 0 plus s times the Laplace transform of f at s.
Where did the negative sign in front of f of 0 come from?
Because we're
Yeah.
I love it that I can just go, excellent. So it just comes from integrating by parts, and it's the negative on the boundary term. Okay, what do you think? Is this a good identity or not? Why is this so nice? Why is this worth time in my class?
Because it converts the derivative into product.
Yeah, it converts differentiation to constant, not bad. So it's like a linear term in S. And here's my Laplace transform. So it's a really nice mix. And so the idea is, if I had a differential equation, if I take the Laplace transform of both sides, instead of having to do a derivative, I now just need to solve for the Laplace transform of f. Not every equation in the world, however, just involves one derivative. Some of them involve two. There's even a few that involve more. It's nice that so many equations in the world only involve two derivatives. How would we calculate the the Laplace transform of f double prime? So one possibility is to go back and have f double prime of t and do from the very beginning.
Or you could just plug in.
Or we can plug in. So we have two approaches. One is to go back to the definition and calculate the Laplace transform of f double prime at s by going through and just doing integration by parts twice. So there's my Laplace transform. Go through it twice. The other thing is, well, let's let g equal f prime. Then the Laplace transform of f double prime at s is the Laplace transform of g prime at s. I'm going to just do this slowly because it's just good to see how the algebra goes. Well, this is then just equal to negative g prime of 0 plus s times the Laplace transform of G at S.
Is that negative G of 0?
Sorry, thank you, negative G of 0, thank you. I'm getting ahead of myself with my primes. But what is negative G of 0? Negative F prime of 0. And now we have plus S. Now the Laplace transform of G is just the Laplace transform of F prime, which we know is negative S. I'm sorry, is negative F of 0, right? Plus S times the Laplace transform of F at S. So we get negative F prime of 0 minus S F of 0 plus S squared Laplace transform of F at S. This is 2 data points. Can you conjecture what the Laplace transform of F triple prime would be? What should that be?
Minus second derivative of 0. Minus S times first derivative of 0. Minus S squared second derivative of 0. Plus S cubed cross transform of F at S.
Perfect.
Would that be just F of S squared too?
Yeah, S
Oh, sorry.
squared.
That should just be F of 0. Yes, thank you. It was said correctly, but written incorrectly. Okay? How would you prove this? Induction, right? This is screaming at you to do it by induction. So what this tells us is if we have a polynomial, if we have a fourth derivative, fifth derivative, sixth derivative, we'll just get a polynomial with coefficients that are functions of f, and then at the very end, we'll have our Laplace transform. So the idea is we can actually use this to solve a variety of differential equations. So how many of you have seen this method to solve differential equations? Okay, excellent. Did they talk about the inverse Laplace transform and the difficulty of calculating it? Right. So just because you can write something down doesn't mean you could actually do it. So, for instance, thank you. Right. So let's say we want to solve, y double prime of x plus 2 y prime of x plus y of x equals. I'll just do it equals g of x. I'll do the general case. Let's take Laplace transforms of both sides. So the first thing you need to show is that the Laplace transform is a linear operator. Well, given that it's the integral of your function against e to the minus st, the integral of the sum is the sum of the integral, so it splits. So you get the Laplace transform of y double prime at s plus twice Laplace transform of y prime of s plus Laplace transform of y of s equals the Laplace transform of g of s. Right? And this is where I wish I had only done one derivative and not two, but all right, so the Laplace transform of y double prime is going to be minus y prime of 0, y double prime of 0, minus s y prime of 0 minus s squared y of 0 plus s cubed Laplace transform of y at s.
Extra prime and s. So that would be the third derivative. You're writing the third derivative.
We still have just what, y prime?
Yeah.
Okay. Okay. Then I think we must have written it wrong over. Oh, yeah, okay. Oh, no, that's the third derivative in the second. Okay, I was just reading things wrong. Okay, good. So y prime of 0 minus y of 0. And I only have one y of 0. Okay, perfect. Good, thank you. Plus, I was looking at the third derivative. Thank you. Okay, Laplace transform of y of s. So that's the first term. The second term would now be twice the Laplace transform of y prime. So it would be plus twice y, minus 2y of 0 plus 2s Laplace transform of y of s. And then the last one is just going to be plus a Laplace transform of y of s equals the Laplace transform of g at s. Well, I've got the Laplace transform of y here. I bring all this stuff over to the other side, and so given that I will do the algebra incorrectly, I will have one of you, or maybe several of you, watching. The Laplace transform of y at s will be the Laplace transform of g at s. Now, fortunately, all these minuses become plus. So plus y double prime of 0 plus s plus 2 y of 0, and then divide by s squared plus 2s plus 1.
Isn't it y single prime of 0?
It is y single prime. See, that's why I told you I'd make the mistake. Thank you. We now know what the Laplace transform of y is. So now y is just the inverse Laplace transform of this. And that's where the meat is. But if you can invert the Laplace transform, you can now solve a huge number of differential equations. And one of the techniques to find these inversions is through complex analysis. And so there's a couple of problems on the last homework where I just ask you to do this. By all means, use tables of inverse Laplace transforms. They exist, just like tables of integrals exist. All you have to do is say, okay, at the end of the day, I have this. Let me invert it and see what goes to this. But how do you actually calculate the inverse Laplace transforms? This is where you use complex analysis. So the tools we're learning in this semester are actually useful for a variety of problems. Okay? So it all comes down to inversion. We are seeing this again and again and again. The other thing is that these transforms are all very much related to each other. So I will end with the Laplace transform. Let's just write it on the board one more time. So Laplace transform of f at s is the integral from 0 to infinity f of t e to the negative st dt. What does this look a lot like? It looks a lot like the Fourier transform. The difference is the Fourier transform would often be at a minus 2 pi I t. This is a minus t. Not a big deal. So really, if you just change where you evaluate them, they're the same. There's also the Mellon transform, which is, again, very similar under a logarithmic change of variables. A lot of books will only have formulas or identities for one of the transforms. And then if you want it for one of the others, then you just have to convert. This is very similar to the change of basis formula. The log of x base b is the log of x base c over the log of b base c. What this means is if you understand the change of basis formula, you only need logarithms in one base to get logarithms in any base. So if I can do logs in base c, I can do logs in base b. I only need one table. If you look at tables of integrals, one of the hardest problems is there are so many different ways of writing down some of the integrals that your version might not be the one the book chose to write. A lot of times books will write multiple versions of the same thing just to make it easier for people to look. One of my favorite stories, and this is a good place to end, is when Kepler was trying to understand the orbit of Mars, he eventually wrote down the equation, I might have said this already, of motion for Mars, and crap, it looks oval if only it was an ellipse, but it's not, it's this object. Well, he had actually written down the equation of an ellipse, but but not in the way he was trained to recognize the equation of the ellipse. And so he had it there, but he didn't recognize what he had. And that's what I really want you to try to be getting out of what we're doing, is you know the math, but sometimes the way things are written, the algebra hides what's going on. And one of the hardest things is finding out what is the right perspective to look at. And that's why I'm really hopping on how to look at mathematics rather than going through material. We could go through a lot more material. You saw the first half of the semester. I have no problem going through material quickly. But I really want to hop on how to apply it and how to look at things. I will hope today that the video audio quality is more consistent. I have no idea what's been going on.